If you haven't watched the plate movement and introduction to margins video, I would suggest you probably watch that one before this, just because the task that I'm asking you to do will make a little bit more sense. I just think it will be easier for you that way. All right, so if you haven't watched that one, stop this one, go back and watch that one, and then come back again. This video is going to be about divergent margins. There are two types that we're going to look at. One of them is under the sea, one of them is on land. So we're going to go through those, and then I'll do another video for convergent and so on and so forth. Okay, what you're supposed to be doing then is you're supposed to be creating revision notes on all types of plate margins. There's space for those notes on pages 19, 20 and 21. But if you don't want to use that, you want to do something different, that's absolutely fine by me. Basically, and I've said this a few times, but I will repeat it, if you can get your head around the plate margins, the rest of the module is much, much, much easier for you. So take your time on this bit and it will pay off, I promise. Right. You may well call divergent plate margins constructive, and if you do, it's not the end of the world. We would rather you called them divergent, but it's not going to fail your geography A level. Okay, so what we mean by divergent is that the plates are moving away from each other. And we have actually talked about the first type of margin because when we were talking about how do we know about plate tectonics, and there was a big turning point, which was the discovery of the mid-Atlantic ridge in World War II, which led to lots of investigation and basically the whole of plate tectonics being worked out. So the mid-Atlantic ridge is a divergent plate margin because what it is, it's a long line of volcanoes under the sea in the Atlantic, obviously, and it's where new crust is being created. And once they discovered the mid-Atlantic ridge, they did more investigating and discovered that there's loads of them. I'll show you a map in a minute. So it's two plates moving apart. You've got a ridge of volcanoes in the middle, which is where, as the plates are moving apart, the magma comes up, because, of course, we know that there's molten rock thanks to our different layers. And you get loads of volcanic eruptions and loads of earthquakes, but because, with a couple of exceptions, which we'll be talking about in a minute, they don't really get noticed because they're under the sea, doesn't really affect people very much, so you don't hear about them on the news particularly. Okay, so this is the mid-Atlantic ridge. Funnily enough, it's in the middle of the Atlantic. But you can see that there's quite a few others of these. So it's by no means certainly the only one. You can also see what this map does, just to pick up on something we did previously. It colour codes the difference between oceanic and continental crust, which I quite like about it. So you get the ages. You can see that the continental crust is much, 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 much older because there is a fixed amount of it. It can't be created or destroyed. So it's been here for a long, long time. Whereas oceanic crust is sort of constantly recycled. It gets created at the margins we're currently talking about, and then it gets destroyed in other plate margins. So it's sort of constantly recycled, and therefore, look, much, much younger. Cool. That's a slightly simplified diagram just to show you all of these divergent margins under the sea. The mid-Atlantic ridge is definitely the most famous of them. And there is Iceland that sits on top of the mid-Atlantic ridge. And we'll talk a little bit more about that in a second. What I want to pick up on now is earthquakes. So divergent margins under the sea have volcanic eruptions, definitely, because the two plates are moving apart, the magma comes up, hey presto, you get a volcano. But if you think about it logically, in a divergent margin, the plates are moving away from each other. Why on earth do you get earthquakes? Because earthquakes require friction. if the plates are moving away from each other, where is the source of friction? What on earth is going to give you an earthquake? So I need to introduce you to these things, which are called transform faults. So this whole thing is the Mid-Atlantic Ridge, but can you notice now that it's actually split into sections? So here's one section, here's another, here's another. The lines in between each section are called transform faults, and they are where you get the earthquakes. Now, this is a slightly sort of zoomed in diagram, and I've also attempted, you'll be overjoyed to hear, my own version on the next slide. So each of these sections is moving away from each other because we're at a divergent margin. But here is where you get the source of friction, ladies and gents. Each of these sections is moving at a slightly different speed. We don't have to worry or care about why that is, but they are moving at a slightly different speed. So what you're going to get between here and here is friction. In fact, each one of these is like a mini conservative margin or a mini San Andreas fault, if you know more about the San Andreas. Because what's happening is you've got two bits of crust moving past each other. That's going to give you the build-up of friction, and that could always potentially give you an earthquake. Okay, but even though we're under the sea, you do not get tsunamis at divergent margins because the movement is horizontal or lateral, if you prefer that word. To get a tsunami, you need the movement to be vertical, and I've got some animations and diagrams to show you that when we get to other plate margins. So even though we're under the sea, we're not going to get tsunamis at these. We get volcanoes, yes. We get earthquakes, yes. We do not get tsunamis. Here is my brilliant diagram. So there's a big line of red in the middle because that's your chain of volcanoes created by the plates moving apart and the magma coming up. So the red is there for the hot bit. Then I've tried to show that each of these sections is moving at a slightly different speed. I've made some numbers up. So if this section is moving at 2 centimetres a year and this section is moving at 4 centimetres a year, you are going to get friction between those two sections, and that is the source of the earthquake. All right. So you get them in all of these places. So all of these are going to have volcanic eruptions. All of these are going to have earthquakes, but notice they're generally in the middle of oceans, and therefore we don't hear about them. They don't really affect anyone. Yeah. Except good old Iceland. Iceland is an island on top of the Mid-Atlantic Ridge, which is a bit of an anomaly. It's because, as well as being on the Mid-Atlantic Ridge, it's on a hot spot. Now, hot spots, I'm going to explain to you in another video, but they are pretty much exactly what it suggests. They are places where the mantle is extra hot, and you get loads and loads of volcanoes because of that. Iceland, therefore, is on the Mid-Atlantic Ridge, and it's on a hot spot. So you are going to get loads of volcanic eruptions. They get, on average, an eruption once every 5 years in Iceland, and they get lots and lots of earthquakes. In fact, so much so, this is a bit bonkers, earthquakes are part of their weather forecast. They're just so much a part of life. Most of them they don't even notice, but occasionally they'll get one that, you know, the ground shakes and things happen. This little clip, I'm not going to show you, but you're welcome to have a look. I've just realised I haven't told you the name of the PowerPoint, sorry. So this one is, it's got a number 3. Oh, it's there, look. Number 3, convection and boundaries. So in the hazards folder, if you find that, you will have access. And this is just a little video about the birth of an island called Surtsey, which you can see here, which was entirely created by a volcanic eruption that you might quite like. And it's there, look, there's Iceland. And because it's on the Mid-Atlantic Ridge, Iceland gets a little bit bigger every year. It's a divergent margin. The plates are moving apart from each other. The volcanoes create new land. Iceland does get bigger each year, which is kind of cool. Right, so that's the first type of divergent margin, the ones under the sea. This is the second type. And there are quite a few similarities for us to understand, but a few differences. The first one being that here we are not under the sea, which is a fairly good clue. So we start off with a lump of lithosphere, a lump of continental crust. And what happens is you get an upwelling of magma for reasons we don't need to go into or understand, but the magma rises and forces its way into the crust, into the lithosphere. Now, because the mantle is really, really, really hot, what it does is it begins to not melt, but it begins to push its way into the lithosphere, and then the two sections get pushed apart. Now, if you want to practice this, if you have a lump of blue tack or a lump of Play-Doh or something like that, roll it into a ball or a lump, and then get your fingers and pull both ends of the blue tack away from each other. And what will happen first of all is that the lump will get skinnier and skinnier and skinnier until it breaks. Well, that's basically what happens here. The mantle pushes its way up into the lithosphere, and then the lithosphere gets skinnier and skinnier and skinnier until it cracks. All right, weird, I know, but there we are. And this bit where it gets skinnier and skinnier is called a rift valley. A rift is like a split or a crack, and that's exactly what's happening. And a valley is a low bit, isn't it? You can have a river valley, you can have a glacial valley, and that's exactly what's happening. You are creating a valley as the two bits of lithosphere are being pulled apart by these enormous forces. And then eventually what will happen, look, is that your two bits of crust, your two bits of lithosphere will be completely separated. I mean, we're talking millions of years, but eventually they will be separated, and you will get water in between, purely because you're much lower down and it's just going to fill up with seawater. And then this plate margin becomes the one that I've just explained to you. So once your two bits of lithosphere have been completely separated, you've got a new ocean basin, and hey presto, it's now a divergent margin under the sea. Weird, huh? And this is happening, ladies and gents, in Africa. So Africa, wait for that to go. Somalia, bits of Ethiopia, etc., are being ripped off the rest of the continent of Africa. So this is the Rift Valley here, and you can see it's absolutely chock-a-block of volcanoes. Well, that's no surprise, because if you've got this mantle that's forced its way into the lithosphere and it's melting its way through, there's going to be a huge amount of magma, and therefore you get lots and lots of volcanoes. So this image, I think, makes it really obvious what's kind of happening here. Africa's being ripped apart, and you get these enormous volcanoes happening. Now, it's going to take millions of years for this for it to be complete, but they've already decided that they will call the sea that forms in between the Red Sea, because basically it will just be an extension of the Red Sea. So they've got the names ready, even though all of us will be long since dead and gone when it finally happens. So there's a slightly different one that you might prefer. And there are a couple of videos there which talk to you about the Rift Valley. The first one is possibly a bit patronising, for which I apologise, but it's the creation of a Rift Valley shown in Play-Doh, which, if you're finding Rift Valleys a little bit complicated, you might benefit from, because it might simplify it for you. The second one is part of a documentary about the Rift Valley, and I would say it's quite helpful. Both of them are 2, possibly 3 minutes long, so they won't take very much of your time at all to understand. All right, so you may have already put this together in your head, but you might not have done. I don't know if you did your jigsaw puzzle of Gondwana land, or maybe you avoided that one, but we know that at some point in the Earth's history, all of the continents were joined together, and that was called Pangaea. And then the next stage was where you had Gondwana land and Laurasia. Let me just give you a page reference to remind you. Page 11, Continental Drift. You've got some maps. Well, how we got from Pangaea to where we are today was this process. Okay, because if all of the continents on Earth were joined together in one big lump called Pangaea, something made them separate, and it's this process that made them separate. All right, so it's been quite important in the story of continental drift. As I said, when the 2 bits of lithosphere have been completely separated from each other, it then becomes the first type of margin we talked about today. It becomes a divergent margin under the sea. And I will probably show you this video so many times you will be just so bored of it. But this, look, is stage 1 of the Wilson cycle. So J. Tuzo Wilson is the scientist who gets the credit for the theory of plate tectonics, even though, and you probably have figured this out, I'm a little bit biased to Alfred Wegener. I think he did all the hard work, really. But anyway, never mind. So J. Tuzo Wilson gets the credit, and he came up with this thing called the Wilson cycle. You've got some diagrams of the Wilson cycle on page 14. This is the first stage, Rift Valley. So you've got your lump of continental crust that gets ripped apart. There's your Rift Valley with loads of volcanoes in it. And then it becomes a divergent margin under the sea. And that is what's happening at the mid-Atlantic ridge, and so on and so forth. All right, so the process of continental drift begins with this Rift Valley, and then it becomes the other kind of divergent plate margin. All right, so a little bit confusing in places, I would imagine, but they are the first 2 plate margins. I'm just going to go back, sorry. Right. So just back to here, we've now done these 2, and you should have some revision notes, some diagrams, a little bit of information about the examples. You've possibly written that on page 19, you've possibly done it in a completely different way. If what I've said hasn't been that useful, I do apologise. There's loads of stuff on the internet about this. And also remember, of course, to send your questions to Nick for his question and answer sessions at 2 o'clock on Mondays. I've said this to you already, but send the questions as soon as they pop into your head, so that they're fresh in your mind, because otherwise you might forget them. Next video, we will go through convergent margins.